many years ago, when I was, I think, in my 20s at university, I started thinking about how we might create a programming language that could naturally handle concurrency. That is, naturally handle the ability to do more than one thing at a time. So this has been a very important part of my work as a game developer, because as a game developer, that's what you do all the time. You're always concerned with making a computer do more than one thing at a time. And it turns out that this is actually a huge issue. When we look at scripting languages in video games, you know, there are many solutions provided. It seems to be very common to sort of start thinking about how we can use something other than C++. You know, maybe you use Lua, or you use, I don't know, C#. Obviously, Unity uses C#. But it's interesting to consider that this programming language, that is any programming language that's used as a scripting language, tends in general to provide one thing that is really important that the native C or C++ struggles to provide, and that is concurrency. So, you know, it's something I used to talk to my students about. It's like, what is the reason for having like C# that runs in a virtual machine? That's a machine that's not on the hardware, but is sort of, well, yeah, it's a programmed machine. In fact, that's the way C# works and Java. Or you can go to languages which are interpreted. An interpreted language, it literally runs the program on the fly. And what these provide is the ability to do concurrency, and really that is it. It's something that I found very ironic, because in 1964 there was a guy called Conway, not the Game of Life Conway, but another Conway, who created the concept of the coroutine. Coroutines are finally arriving in C++ in, well, 2020. No, that's the standard. We can assume that we can start using them in about 10 years from now. Why it's taken so long, this is a mystery. I started using coroutines back in around 91 when I was developing the football game Goal, and I implemented them with macros in assembler. But yeah, I digress a little bit, but not that much, because I'm highlighting a central problem. Concurrency doesn't come very easily to programming languages, and because it doesn't come very easily to the underlying architecture, to the microprocessors. And in fact, our languages, the ones that we use that you know seem to do a lot of the heavy lifting in software engineering, for example Linux, the Linux kernel, it's all written in C. These are all fundamentally tied to the architecture of the computer, and this is a reason for their efficiency, because they, you know, they kind of, it's going with the grain, so to speak. But the problem is that grain has a real issue connected with it, and this issue has to do with the fact that, or the way that I look at it anyway, is that computers were originally designed for doing calculations. They were like glorified calculators. If you look at some of the early calculators that existed, they were mechanical in device before the electronic ones came along, and you can see it really, it's kind of interesting to look at those, because they really highlight how when you did an operation you would set it up and you'd hit a button and it would perform the calculation and then it would stop. Yeah, unless you divide it by 0. You should check on YouTube for mechanical calculators. There's a wonderful demonstration of dividing by 0. And they had to provide a special button in case this happened. You could stop. Also, because the divide could take time, so you could stop the divide. But when you think about it this way, a computer is, in the traditional sense, well, let's say from the viewpoint of Alan Turing, from the viewpoint of von Neumann or Neumann, computers that we use today are all based on the architecture, the von Neumann architecture, and that is intricately connected with the Turing machine, or Alan Turing's abstract representation of a computing device. And what these have is a thing, in the end, called a program counter. It really doesn't matter what you call it or how it's represented. When you look at a Turing machine, what you have is an infinitely long piece of tape. It's a theoretical machine, right? You have an infinitely long piece of tape and a head on it that can read and write that, read from and write to that tape. And this head moves backwards and forwards along the tape. And it turns out that with this formulation, you could make any computation that you like. And so that's why, to this day, when you create a new programming language, the question is it Turing complete? If you can prove that it is Turing complete, then you can prove that you could, in principle, program any algorithm in it. And so, and I highlight this because it goes all the way back to the earliest days of computing. We are still influenced by that. Now, of course, that isn't the only sort of program architecture, computer architecture. I mean, the computer architectures, they are this way, but you can build a programming language that sort of, because you can program any algorithm in a Turing complete language, you can create a new virtual architecture. So we're not, you simulate it by algorithms within a computer and with a programming language that is traditional. So this is exactly what happens with, say, functional programming languages. Functional programming languages do not run on functional computers. They used to when we had analog computers. So the great thing about an analog computer is it was actually functional programming on hardware that was in itself functional. But these days, if you work with functional programming languages, you need to remember that in the end, it's running on a machine that is not functional. The difference between the two, functional and non-functional, play on words there, functional and imperative paradigms, if you will, is that in the functional paradigm, you basically make a set of mathematical declarations, you provide an input and you get an output. In an analog computer, you could do all of that and you get a result theoretically instantaneously. In practice, there would be a delay as it propagated through the electronics, but the delay would be actually quite short. There certainly wouldn't be a sequence of calculations in an order in the way that a computer does it. For example, you could have something that summed two voltages together. 3 volts plus 2 volts goes into this box and out comes 5 volts without any need to do any algorithm, to do any processing. It just would happen in one go. But computers that we work with, in practice today, the digital computer doesn't work that way. To add 2 plus 3 actually executes an algorithm. Is actual logic inside the CPU to achieve the result. And it's all driven by the clock. So, we're all familiar with clock speeds. The general measure of how fast a computer is it's how fast its clock is, how many gigahertz these days. So what happens is that when you ask a computer with a von Neumann architecture to add two numbers together, there is an intricate little machine that runs, electronic machine, that is similar to the mechanical machines, but just runs very, very fast because it has no moving parts, unless you think of electrons as moving parts. And it just operates really fast. And just like in the mechanical calculator, there was a motor that would turn the machine over as it operated. You have the clock in the modern CPU, the central processing unit, right? There's a clock that ticks the intricate little electronic mechanism and processes an algorithm, and you get the result. And it's really important to understand that this model of a series of instructions and a clock and executing these instructions one at a time, that's executing a computer program, is something that goes all the way back to even the earliest mechanical machines. It's still the same principle, and it's an ordered set of instructions. And this is imperative. In the sense that imperative programming languages, however, whatever their syntax and whatever their philosophies and object-orientated this or that, or no matter how much it tries to hide the concept of the program counter, which is a very fashionable thing in languages today, try to pretend that there is no such thing as a program counter. You can't access the program counter in C or C++ unless you resort to trickery. And C# completely denies its existence. But it's important to realize that it is there. And so that even a program an imperative program that has no state, as in it has no variables, it still has state. The hello world program in C still has state. Even, you could say, of course it has state because internally it works, but I mean, from the language point of view, you say printf hello world, right? And it looks like there was no state, but in fact there was, because first of all, it had to enter the function, and the program counter had to arrive at the print statement, and then it had to print the statement, print whatever the print statement was printing, and then it had to get to the next instruction where it would return from the function or exit or whatever it is. So in fact, what you run the program and it prints hello world, but in actual fact, there was state involved in the program counter, but this is sort of fudged over. What this means is that when you're writing programs in an imperative programming language, the order of your instructions are really important. So I just